missing? What will be missing? There are some isometries which do not correspond to motion, continuous motion in any direction. What would it be? Every vector is mapped to is negative. It's something like this sphere is reflected in its center. That one is also an isometry, and that isometry is together with this, and in all their combinations. And group theory is called what? Least product or direct product. Another good example is modern. This is quite classical. Modern means it has something to do with graphs. But we haven't defined graphs as we're getting there after second part of slides. But anyway, we will just draw it. We'll just draw it. And I don't want to always restrict myself, my own freedom to finite, undirected simple graphs, which all the graph theorists probably in Pakistan, they even restrict more. I don't like that, but during the interview, even that part is not very well understood. My major interest since 2012 is the graphs which are locally finite. I will give one example. Gaussian plane, Gaussian integers. Which is a ring of integral domain and with other domains as well. Gaussian integers, the ring of Gaussian integers, you can draw it. And the graph theorists usually don't know Gaussian integers, they call it grid graph. But it is not grid graph because it's going infinite all in all the four directions. But I'm an accountant who is making a table. Not a table. 0 is here, 1 is here, 2 is there, 3 is there, 4, negative 1, negative I, right? Gaussian integers. It gives me a nice metric space. This metric space is defined by now we only have n equal to 2. So z squared is the, for this graph, it's a vertex set. And the edges are given by all unit vectors. When I teach linear algebra to undergraduate students, I usually, as soon as we define vectors and go to infinite space, I want to usually teach the young students how many unit vectors are there in this space. You have to quickly answer. How about the real line? The real line, how many unit vectors are there? 2. In the real Euclidean plane, how many unit vectors are there? 4?
Infinitely many.
Yes. It's a continuum many unit vectors are there. Everything which ends on the unit circle. Unit circle again.
Yes.
Unit circle again. And for any n, at least 2, it is continuum many unit vectors, if it is finite dimensional. How many unit vectors are there in this ring? This is not a vector space, but there are unit vectors in this. How many are there now? Your answer is now correct. How many are there? 4. Those which have names 1, it's obvious. This one, that one, and this one. Only those 2 or those 4 Gaussian integers have modulus 1. Others have modulus not 1. Actually, in this case, modulus is, there is no modulus which is smaller than that. So there are 4 unit vectors in there. So these four unit vectors acting on with every Gaussian integers, it will give all these four edges. All these four edges. And these four unit vectors satisfy certain conditions. Identity under multiplication is a ring, therefore there is a multiplication. Multiplicative identity is what? 1. 1 has to be, this is addition. In additive ring of this. Additive abelian group, identity is 0.
Yes.
0 does not belong to the set which we call S. If some element is in S, then its inverse must be in. Its negative must be. If this is in negative, that one. If that is in negative, this. These two are negative to each other. So the negative is in, which is equals negative of S is equal to S as a set. The first condition, this is the second condition, first condition. First condition is this V is generated by X. V is generated by X. So this is a finitely generated additive abelian group with respect to addition. And it is a ring. There is also multiplication. Now this is a metric space. The metric is given by, for example, let us consider some points in the space. Let us somehow arbitrarily choose. Of course, as soon as you choose it, it is no longer arbitrary. Arbitrarily choose, and the distance. Distance is the graph here is shortest path length. But here it can be given by the generating set, no problem. So from here we can actually travel 1, 2, 3, 4, 5, 6, 7. Or 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. The shortest path connecting two points is not unique, not necessarily unique. What is the group of isometries? This space is called X. I think we will not do it. We did it somewhere. This is exercise question 3. I'm leaving most of the difficulties to you now. You shouldn't really look down upon these questions as seem very easy. You shouldn't really also not be afraid of it because it looks very hard. It doesn't. Group of isometry. Also, you can actually add a condition that F0 is 0. Those which fit your object. Can you give me a non-trivial isometry? Non-identity. These two you can give me. This is a line, horizontal line, x-axis. Reflection on that. And reflection on the imaginary axis. These are these two non-trivial isometries. We will move to now, one example. Now move to next, which is continuous ones. If I didn't remember the order incorrectly. So we define continuous markings, their basic properties, and little more. Oh, there are lots of nice questions there too. I will remember to write it down. Some of these questions you can find online. Some of these questions you can't find online. So you don't waste your time first to search. Second paragraph is continuous markings. happens from the metric space to matrix. So we define the concept carefully. And have you ever seen any definition of a limit or continuous mapping without using epsilon delta language? Without using for any given positive number epsilon delta and so on. Have you seen any in the courses? Probably first batch haven't seen yet. Yes, what is the topological definition of a continuous mapping?
For every vector in codomain there exists, for every element in codomain there exists an element in domain. For every neighborhood of that domain, f of u is contained in that neighborhood of u.
It simply says it's the inverse image of
Yes.
every open set. It's open.
Yeah.
That is one very economic definition mathematicians worked out through formalism.
Yes.
And I would like some more other definitions which are not through formalism.
Bounded?
Eh? Yes. Sequence is another one, the counter approach to analysis, real analysis. The counter bit is like that. Anything else? I think I can give you at least 5 very different but equivalent treatment of continuity, limit, these concepts. But these are, each of them probably is separate course, so we can't really discuss on this. For example, non-standard analysis way of defining this I really like because it starts from something like a semester of algebra, and then using the algebra you define limits and continuity. It doesn't involve any epsilon delta or open set concept. So here we're going to use the epsilon delta, the Cauchy-Weierstrass way of doing continuity. Cauchy-Weierstrass. Let's hear the metric spaces. And this is the second most general way of doing continuous mapping. So the first most proper general way in topology. And then just next to it is the metric space. So it's good enough in my opinion because if you know continuity concept in metric space, then you can cover most of the functional analysis and real and complex analysis. Metric spaces with their respective distant functions. These are distant functions for rho x, these are rho y, and this with distant function and f clear mapping. If this space is a vector space and this is the ground field, what do analysts call these mappings? If this is a vector space and this is a ground field, the function theorist analyst will call it some name. Functional. If this is a vector space and that is a vector space, it is called operator. I never use those 2 words. They are just making too much. They are just mappings. Only that when you have different spaces, you're giving different names. The reason that they kept up those terminologies that they studied those things first there before the concept of mapping was formalized. So that we can respect. So this is a mapping. If for any real number, when I write inequality signs with real number, also because if there is a real positive real number, there exists a positive real number delta, epsilon delta thing. Many people were killed by this type of analysis. such that for a we should just will not study for a such that it is continuous at x. X minus y. No, the distance is now within norm. So x minus y, s tan delta implies fx minus xy. Usually this y is written before. It doesn't matter because it's norm. S tan epsilon. Then we call this marking continuous at x. Because here is a universal quantifier for y, it's something nearby. So we call it continuous at x. If it is continuous at every point, then we call it is continuous on x, in x. I will omit this part. I'll omit this part. Now, this is the definition of continuous markings. As soon as continuous marking is continuous, you can't prove one thing. It's very elementary. What if you have a convergent sequence which is convergent inside convergent sequence in x, and mark this sequence term-wise to the other space y? Then that sequence is also convergent. And if this sequence is convergent, then that sequence is also convergent. This is for continuous marking, the elementary problem. So this is one of the theorems which I call theorem number, propositional theorem. There's a statement there. If the sequence x is a sequence that converges. Oh, I really like it more economic. If x is a sequence, even more economic if I do that. The main premise is that f is continuous. If f is continuous, this can be proved. And I think the proof is in the slide. We can prove. This can be proved. No. Now each term of the sequence, if their distance is small enough, then their each distance is also small enough. It is continuous. How about the converse? So if this is just a one-way implication, write this as a something. Okay. Most importantly, there is another stronger concept of continuity. What is it?
Uniform continuity.
Uniform continuity. Of course, there are much more in analysis, but uniform is one of them, very important. So we're now going to try to define uniformly continuous, but from a metric space to another. My teasing question would be, let us just consider from this space to itself, what are the continuous markings like? This is a metric space, right? This is a metric space, you can easily verify, and this definition doesn't assume anything other than metric spaces. What kind of marking from this X to itself is continuous?
Which preserves the path. Which preserves the path.
Didn't understand. I didn't understand. Say it again.
जोर से बोल दो यार, कुछ नहीं होता.
Which preserves the path at distance.
Which visas?
Preserve.
He's telling that it preserves the path. Is that what you're saying?
Yeah.
He's talking about the path. The path that we know that.
Yes.
The path.
Give me one example of a continuous mathematics. Just one example. Identity mapping is definitely continuous.
Yes.
Those relations are continuous, right?
And any constant mapping is also continuous.
Constant mapping is also continuous. So there are some non-trivial examples of continuous mapping, but you need to really relate the concept of continuous mapping with its isometric group and its automorphism group. So there are two groups involved, and those two can be proved to be isomorphic. So the thing is that when you look only inside analysis, you probably didn't find anything unusual. And as soon as you look back to more simpler things, then this is meant to be simpler. You suddenly find lost or something. So you have to really go back and forth because we are talking about metric spaces, we're not talking about functional analysis. Now, uniform continuity. So let X, Y be metric spaces. Here and then with their functions and with their distances and F their mapping. And uniform continuity says that if for every epsilon, any epsilon delta language, can you think back what is uniform spaces in topology? What was the definition? It has something to do with one of the 5 separability axioms, right? I think it's every 2 closed sets can be separated. Is that what uniformity means, Dr. Fine? Remind me? Topological uniform spaces. Its definition is given by one of the 5 separation axioms. I forgot which one. Maybe it's one point and another closed set. Maybe it's 2 closed sets. The first 2 closed sets uniform. Another one is called regular spaces. And one of them is called normal spaces. And if it satisfies just 2 points being separated by 2 open sets, it's
also
just
Hausdorff space.
and plus another condition is Hausdorff space. Yes. So the topology has done this economically, but please look back. I don't know, because I have to read and understand. Now here we're looking at the epsilon delta terminology. For every epsilon, there exists a delta, such that for every xy, in X, their distance, oh, this is metric space, so I shouldn't have written this here. This is Euclidean space. Nobody complained. Let me correct. It's fine now, I think. Now I think about it, it's rho xy, small delta will technically imply rho fx y.
X comma y, not x minus y.
Right?
We rho of x comma y.
Yes,
Yeah, rho x or comma, yes.
yes.
And it's also comma. Thank you. Even in epsilon delta language, these 2 definitions look very similar. Where is the crucial difference?
This is independent of point y. Second one.
Third one is independent of what?
Second one is independent of point, but first one is depend upon y.
Yes. First one is x is not quantified. Y is quantified. Here it's any two points, x, y. Does it look something like, for sequences, what does it look like? This is something like Cauchy sequence definition, because here any two terms. Here or uniformly continuous. In the real valued function of one real variables, or in one complex valued function of complex variables, what does uniform continuity really give us in analysis? In analysis, what does uniform continuity really imply and give us really good facility so that we can deduce lots of strong theorems? What are they? The number one must be what is called Heine-Borel theorem. Heine-Borel theorem said that every continuous mapping from a compact space is uniform continuous. That there is a continuity implying uniform continuity, but uniform continuity implying what good things we have in analysis. Have you ever had this kind of question in your analysis? So let us say one variable. So and this one converges to something. And you want to take limit outside and put the limit inside. If this is uniform convergence function sequence, then you have, otherwise you can't do it. Term-wise integration of a series, it relies on this. Term-wise differentiation probably doesn't require uniform continuity. It's because it requires differentiability, otherwise you can't term-wise differentiate. You need to go back to analysis and really see, apart from the Heine-Borel theorem, which was also proved by Kronecker earlier than them, I have the years in the slides. That is the only thing which we are citing in this course. You need to also know that what uniform continuity, general question, this is not exercise. What kind of facility? Facility means easy. Does the uniform continuity give us in analysis? This is a very easy question for us in a job interview, by the way. You will immediately know that whether your background is really strong or not. Job interview. I like Imran. I like Imran very much because he asks non-stop questions. I would love to have him on my job interview. Then we will discuss 2 days, maybe 1 week, and we'll learn from each other. Imply in analysis. Give me 2 examples, and then we will probably give one of them is that one. There are more several more of them. So if you can point out 2 or 3, then you already studying them. But without knowing, you can't really answer that question. So uniform continuity was introduced. It was being used to deduce those theorems first by the famous mathematicians in a very secret way, because they don't state what is they are using, and then they say here it follows, and then the result comes out. And then people, the careful readers will also question from what you are deducing. And then they started working on that, and then at the end they figured out it is this. So they introduced into analysis text, and then now every student is suffering from it. You have to know how it came. And then you know that it was originally written by some, even today's papers, I have to say that many papers are false. Because I can't really see if I'm reading, I'm very slow guy. If I'm reading, I can't really go from 99 sentence to the 100. Obviously, and after this, clearly it is true. And it doesn't follow from the conjunction of the preceding ones. So if I can actually produce it, say this, offend the author. Or if I can really I'm good enough to manage to find out the counterexample, then the author will be convinced. And then he has to continue to work. Nowadays, the refereeing of paper is extremely complicated, and some people don't referee. So the next one is Heineborel. Also Chronicle. Chronicle was early. The years are in the slide. It says continuous mapping from a complex space, uniform. And there is a good book where you can, every first, the analysis, good analysis will contain a proof of this for one real value function of one real variable. That's enough, because that idea is the same even if you go to topology. So that I recommend in the reference section I give is archival of the recent analysis textbook. I met that guy once, here actually. I asked him what does archival mean. He was a Mongolian descendant. Because in Mongolian, archi means alcohol. Archival means alcoholist son. He said, son of an alcoholic. Archival Sadovich Chumarikov has lectures in analysis. And that book is already translated into English. I have a copy, Russian copy on my devices. You're welcome to have it. This book I give page number where the Heineborel theorem is proved. Next. So continuous mappings. Okay, continuous mappings, we need some examples. Topology class will have lots of good examples, because if one of the, if this space is discrete, and that space is any space, then any mapping is continuous. Any mapping is continuous. If this space is any space and that space is concrete, then any mapping is also continuous. And lots of other discrete examples in topology. And you should really check up on that.
Yes, sir, what is concrete matrix space?
Concrete matrix space is every Cauchy sequence converges.
Oh, yeah.
Cauchy sequence doesn't necessarily converge. But if every Cauchy sequence converges, then the matrix space is all complete. Convergent definition was given last time. The test in the United States.